Hello everybody and welcome to this lesson on vectors in plane and space. This is for multivariable calculus, also known as calculus 3. This is our first lesson that we do, and what we do for not just this first lesson but most of this first chapter is we cover a lot of vectors and we start to introduce what 3-space is. There is very little calculus going on for this part of the course because we first need to build the foundation of vectors and 3-space. And vectors have a huge role in calculus, in 3-space calculus, so we need to start to build that up a little bit for you, teach what vectors are. If you have a physics background, this first lesson should be a bit of a breeze to you, but I do want to make sure that you know the correct notation for what you use in calculus. It could be a little bit different than what you've seen in a physics class. So we're going to mostly touch on 2-dimensional vectors. We'll do a little bit of 3-dimensional vectors today, and then we kind of just go from there. So thank you so much for joining, and let's just start learning about this stuff. I got 3 important boxes of information here. So first up, a vector is a set of all directed line segments from points P to Q, also known as a vector. So the bold notation, I'm going to talk about the notation real quick. The bold notation means vector. Because you and I can't write in bold, we can type in bold, but we can't write in bold, we put a little arrow over that. So if you ever see these notations, this is the same thing. The little arrow means it's going to be a vector notation, or bold means it's vector notation as well. So this is vector PQ. Initial point is P. The terminal point, also known as the final point, is Q. Whenever we find a vector, we always do final minus initial. Okay, which kind of brings me up to this green box right here. If we have P and Q, the component form is known as this part right here with these little chevrons on the end. I also can call that chevron form too. So these are chevrons, these little pointy brackets right there. But you do the final minus the initial. If you're in unit vector form, this might be new for some of y'all. Unit vector form means that the distance is 1. So we have I, which is going to be the horizontal unit vector, which is also known as the vector 1, 0. We can see that right down here. And J is the vertical component, which is the 0, 1 component form for J. So just 2 different ways just to name the same thing. And if we want to start talking about vectors that are in 3-space, component form would just be 3 sections. But the unit vector form will have an I, a J, and a K, where the I is in the horizontal, J is in the vertical, and K will go towards the Z-axis, which is something we'll tackle at another lesson. Some important properties. If you're adding or subtracting 2 vectors, all you do is just take each component and just add them up. So this is just in n space, which just means that we don't know if it's 2-space or 3-space or heck, even 4-space. You just take each component and add them up in each space. If you have scalar multiplication, you have k times v. You just multiply this k value by every single component. And then this notation might be a little bit different for you. Maybe it's the same for physics. But this is known as the magnitude, the double bars around the vector. You're going to take the square root of the sum of all the squares of the components. And that's going to give you the vector length, also known as norm or magnitude. I think physics says norm. But hey, let's actually get to our first example here so we can understand what's going on. So here we go. Find the component form and the unit vector form for the vector v that has an initial point of 4, -6 and the terminal point -2, 2. So I'm going to give 2 answers. I'm going to give one answer that looks like up here in this green box and right below that part. So it's always final minus initial whenever I do this. And direction does matter for vectors. So make sure you do this in the correct order. So for vector v, so if you notice, this is just in my notation. This is vector v. Again, I'm not going to write this in bold, but I put the arrow above. I just do the one-sided arrow because it's how I was taught, and heck, I'm going to teach it to you too. I don't do the full arrow. I don't got no time for that. So in the vector form, I'm going to do final minus initial here. So I'm going to do -2 minus 4, and then I'm going to do 2 minus -6. So that's going to give me the vector of -6, 8. I can also write that as -6i. Since I is a vector, I put an arrow over it. If you notice up here, I is bold, so it's a vector. Plus 8j. So instead of giving these dots, I just put the arrows where the dots go. Again, I don't got time for that. Let's go ahead and find the length of vector v now. So what we're going to do is we're going to, well, first notation, so double bar of v. is equal to the square root of, I'm going to square the first component, so the first component here is -6, so -6 squared, plus, I'm going to go ahead and square this second component right here, so 8 squared, and it's going to give me a square root of 100, which we know as 10. All right, let's talk about normalizing vectors here. So normalizing vectors is really finding unit vectors. A unit vector has a length of 1. So in order to guarantee that we have a unit vector, you can take any vector that you have and divide it by its length for each component. And this is guaranteeing you that you'll have a vector of length 1. It will still go the same, the vector direction will still be the same. So let's say that I have some red vector here, just whatever. I don't know what that length is, but let's say that I want this vector to have a length of 1. Then we can change it into the purple vector. I'm just making it a little bolder so you can see it. And let's say that purple has a length of 1. So we can change it from red to purple where they're facing the exact same way. The vector is the same direction. We just change the length. Okay, so this works for 2 space, 3 space, whatever space. So for example 2 here, let's go ahead and find the unit vector in the direction of v and verify that it has length 1. So let's go ahead and find the vector length here by finding the magnitude. So the first example here, I do have -3 squared plus 4 squared, and that's, if you know the Pythagorean triples, you know this answer is 5. So then our unit vector here, I'm going to make that u, which stands for unit vector. I'm just going to take each component and divide it by 5. And this gives us a length of 1. This does ask us to verify, so I'll totally verify this for you. If I were to find the unit vector of this, so -3/5 squared plus 4/5 squared, that would give me 9/25 plus 16/25, which is 25/25, which is 1. Square root of 1 is 1. We just verified that this unit vector has length 1. Go ahead and move on to the next one. So now this is a vector in 3 space. I'm gonna hold off on drawing this out for you. The next lesson will cover that, but we're just gonna find the unit vector for this and then we'll verify it. So the length of this vector is gonna be each component being squared. So the first component is 2. Second component is not 2, it's actually -2, so just be careful of that. You'll get lucky if you miss that, but that -2 right there indicates we have a -2 here. If you do this math out real quick, you'll see that you're going to get square root of 9, which is going to be 3. So now let's go ahead and rewrite this vector as u. So this is going to be, since the question is asking this in the IJK form, the unit vector form, I'm going to do the same thing. I'm not going to change the way I write the answers. -2/3 j plus 1/3 k. All right, that's a fantastic answer. Do you want me to verify that? Oh, sure, I will verify that. Thanks for answering that question. You can probably verify this yourself, though. So we're going to do the first one squared, which is going to be 2/3 squared plus -2/3 squared plus 1/3 squared. That's actually going to give me square root of 9/9, which is equal to 1. So those are both unit vectors of length 1. For this next problem, we're going to go ahead and find the components of v as shown below. So we do have points. This is in 3 space, by the way. We do have this, I don't want to say it's cube, but box. Maybe not all the sides are equal. So it gives us points, which is great. So we can actually find what the, I'll color code this as well. We can actually find what AB is. The vector AB. And then what I want to do there is I want to take the vector AB and I want to shrink it down to this blue size right here. So this is what I got to do to shrink this down. We just learned that we can shrink any vector down by finding the unit vector. So let's go ahead and do that. So we're going to find the unit vector of AB. And then once we do that, we can take that length and multiply it by anything to get any other length that we want. So what we need to do is we need to find the unit vector, and once we have the unit vector, we can use that to manipulate this any way we want. So, and I'll verify it afterwards as well, make sure that we do have the correct answer. Let's go ahead and find the vector AB. So in order to do this, I'm going to use component form. I'm going to do final minus initial here. So I'm going to do 2 minus 0, 5 minus 0, and 0 minus 4. So I'm going to get 2, 5, negative 4. I'm just multiplying each of these components. Okay, so it's final minus initial. So 2 minus 0, 5 minus 0, 0 minus 4. Once I get that, I want to go ahead and find that length. So that length of AB is going to be equal to the square root of 2 squared plus 5 squared plus negative 4 squared. This isn't as easy of numbers as the other one was, so I will work this one out a bit. You're going to get root 45. I guess we can break that down if we really want to 3 root 5. You don't have to, but maybe it's easier. So I can rewrite this red vector, I'll change it to green now, as a unit vector by dividing each of these by 3 root 5, so 5 over 3 root 5, and then negative 4 over 3 root 5. So that's going to be this green vector right here. It's going to be kind of hard because I doing this over the v, but this is my green vector. That's my unit vector. Okay. Now, how do I get this green vector to be blue? Well, since I have the length here as 1, if I multiply this length by root 5, it's going to give me a length of root 5. So let's go ahead and do that. So to find v, that's just going to equal 5 times, or sorry, root 5, because I want the length to be 5, times root u, which if you remember from our previous page here, we can multiply by a scalar value. It's totally fine, totally legal. So I'm going to go ahead and rewrite this now as 2 root 5 over 3 root 5, 5 root 5 over 3 root 5, negative 4 root 5 over root 5. Would you happen to notice that all the root 5s, they're all going to cancel out? Oh, and there should be a 3 down here, so negative 4 thirds. And there you go. That's going to be our vector v. Do you want me to verify it just to make sure that this has a length of root 5? Because I totally can. What's that? You want me to? Sure, why not? So, if I find the length of v here, square root of 2 thirds squared plus 5 thirds squared plus negative 4 thirds squared. So I should get a 5 inside of here. We're going to get 4 ninths plus 25 ninths plus 16 ninths, which is going to end up with root 45 over 9, which is going to be root 5. The 9's in the square root too. Everything is the square root here. Okay, so I verified it for you. All right, let's go ahead and move on to our last section here. So, if you use a unit vector, and theta is the angle measured in the counterclockwise from the positive x-axis to u, then the terminal point of u lies in the unit circle where u is going to be cosine sine, which, by the way, we can verify that that is a unit vector that does have a length of 1. So hopefully this is something that you have done in pre-calculus and to possibly talk about this in calculus as well. But if you have a vector, which really could be written as parametric equations of cosine, x is cosine and y is sine, the r value is 1. So that's why we have a unit circle right over here. So you can kind of look at this picture over here. This is very wordy, this green box is very wordy. All we're just trying to say is that we have a unit circle and theta is going to start from the positive x-axis. Okay? And because of this, we can rewrite v as multiplying each of those components of that vector by the length of v. So it's going to look like the horizontal component is going to be the length times cosine theta, and the vertical component is going to be the length of v times sine theta. That should look kind of sort of familiar when we did polar. If you remember, for polar, the x-coordinate, which is horizontal, by the way, is r cosine, and y, which is the vertical, is r sine. So this should look somewhat familiar, at least you can compare that. Okay, so we're going to use this information on that box above to answer this question, and I'll draw this out for you a bit to help you understand what's going on here. We have an airplane with an airspeed of 400 kilometers per hour and is headed east, and there is a northwesterly wind of 80 miles or 80 kilometers per hour. That just means that the wind is blowing towards the southeast. So we got 4 parts here. Really, these parts are building up to really answer part D. So find a vector representing the velocity of the airplane in the air. Now, if this airplane is going directly east, so if I were to just draw a coordinate axis right here for you, that's what I do for all of these. I draw a coordinate axis. Let's have the airplane be red. And this is going just east, if you kind of want to know how this works. This is going to go east. Oh boy, that's not a straight line at all. It's going to go east this way. Okay? That's very clearly an easy vector to notate. So I'm going to say this vector sub A, I'm going to use A as, airplane, is going to be, it's just going east, so it's going only horizontal, not vertical at all. This should be 400, 0. It's not going up at all. It's only going to the right. If it was going left, if it was going west, for instance, that'd be negative 400. And this does have a length of 400 too. I did not need to use my formulas for this whatsoever. We'll change right here for this next problem. Find the vector representing the velocity of the wind. So again, I'm going to draw my axis here. And when I talk about the wind, I don't know, blue wind? Sure. This is going to go towards the southeast. So southeast is this way. So I have to figure out what this angle measure is from here to here. So what is that theta value? Now, there's two answers I'm going to give you. If you've been doing AP Pre-Calc and AP Calculus, we didn't talk about degrees at all. If you talk about physics, physics is all in degrees. So I'm going to tell you right now, this is 7 pi over 4. Same thing as 315 degrees. I don't care which mode you use, just make sure you're being consistent. I'm going to stick with the 7 pi over 4 just because I'm used to the radians. I'm a calc teacher, so I'm going to stick with that. So for our velocity of wind, or vector for wind, I'm going to get for the horizontal component there. We know it's going to blow 80 kilometers per hour, so we're going to go 80 times cosine of 7 pi over 4. And then the vertical is going to also be 80. And that is going to be sine of 7 pi over 4. I'm going to do a little bit of simplifying here, and I'm going to get this to be 40 root 2. And this is going to be negative 40 root 2. Which should kind of make sense because if you look at this vector right here, we are going to the right, so we are positive. And vertically, we're going down, so that should be negative. Just because I will have access to a calculator for a problem like this, I'm going to go ahead and tell you what this answer is in terms of decimals, because we're going to start adding everything up here pretty shortly. This is going to be 56.568. I know there's more decimals than that, but I'm going to just stick with the 3 right now. As I start typing these answers in and working through the rest of the problem, I'm just giving you a heads up that I will be using all of these decimals. I won't just be using just part of these. Part C is asking for the resultant. So let's go ahead and do that. I'm going to label that as, I don't know, green. But actually, I want to show what's going on here. So we have the plane going in this direction, east. And then in blue, we have the wind that's blowing it this way. I'm just trying to be... So red is definitely much longer than blue, because red should be 400, blue should be 80. And so we'll go from right here to right here. I guess that's somewhat accurate. So this dotted green line right there, that's my resultant vector. And so with the airplane getting pushed by the wind, the actual airplane is going this way right here, where green is. So this is my, I'm going to label that R. So V sub R. So this is my vector of my resultant. All I'm going to do here is add up my component. So I'm going to do 400 plus this 56 something. That's going to give me 456.5 0.568, comma 0 plus this negative right here. So we're just adding these vectors together. Negative 56.568. And that's my resultant. I'm going to be using that vector to answer everything for part D. So part D says to find the true speed. True speed just means that I'm going to find the magnitude of the resultant. So, I mean, we can kind of predict this answer a little bit here. If the airplane is going 400 and then the wind is pushing it 80 kilometers per hour, kind of sort of the same direction, like right here, like it's going easterly. It's not going against it. So I would guess that this number is above 400, but yet below 480. So it's somewhere in there. It's being pushed, not against it all. So it's somewhere between 400 and 480, just as I'm predicting these answers. So now, when I go to my calculator, I'm going to type in every single digit they got here. So that's what that dot 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 means. I'm not going to just type in the 3 digits right here. I want to make sure I have a good answer. Quite honestly, I would probably type in the 40 root 2 plus 400, just so I know I'm good to go. Plus, and then for this one, I would probably just type in the 40, the negative 40 root 2. That's what I would do. But I want you to know where these numbers came from, so on your notes. So here you go. If you were to do this math, you have a calculator at your disposal for questions like these. I'm going to end up with 460.059. I did this already in my calculator. Kilometers per hour. So my prediction was pretty accurate. Okay, it was between 400 and 480. Direction of the airplane. So I want to find the direction of this dotted line right here. So really, I want to find that theta value, and then I will take that theta value and I'll relate it to the southwest stuff. That way you can see what that looks like. So the direction, it doesn't say it up here, but their direction is going to be tangent of theta is equal to the vertical component over the horizontal component. Okay, so when I do that, I'm going to end up with negative 56.568. There's more digits in there, and then this 56.568. There's more digits there. This is going to spit out a negative value because tangent's negative. So if we do inverse tangent this number can only produce values that are in quadrants 4 and quadrant 1 from the positive x-axis, which means we can only be negative or positive between negative pi and pi, because again, I do this in radian mode. That's just me. We're going to get a radian answer of, actually, I'm not equaling this. This is just when I solve for this. So when I solve for theta here, it's going to be inverse tan of that. I'll write it out. Inverse tangent of this negative 56. There's more there. And this 456. Again, there's more there. I got an answer of negative 0.123 radians. It's fantastic. If they want to know what this is in terms of south and east and west and north or whatever, this is clearly going, that's why it helps draw the picture, clearly going southeast. So now that I have the radian answer, I do want to convert this to degrees just in case you ever get asked for this in terms of degrees. So to convert from radians to degrees, you just take your radian value and multiply that by 180 degrees over whatever pi radians you have. That should be a pi in the bottom. And that's going to convert that to degrees. Okay, so if I do that for this value right here, I will end up with negative, I have it somewhere, 7.0629 degrees, which is a totally awesome answer. And if we want to, let's go ahead and look at the direction that we have here. So since our direction is going southeast a bit, you can notice it right over with the green, that is going to be south. It's south of east by 7.0629 degrees. So all you do is just state the direction. So it's going south of east by that much, okay? If you're going above east, that'd be north of east. If you're going below west, that'd be south of west, and so on and so forth. So that's going to wrap up our video here. Make sure that you like and subscribe for more content.